Hello again, it's Dr. Armand. Today we're going to be doing another lecture on general chemistry. Today's topic is Le Chatelier's principle. So what kinds of things can we do to a system in equilibrium to cause a disturbance in the equilibrium? And then how does equilibrium react to reestablish equilibrium? So I hope you enjoyed today's lecture. Sit back, relax, and let the sounds of chemistry take over. Let's get started. Oops. I'm back. Now let's get started. Like I said, today we'll be looking at Le Chatelier's principle, the last part of the chapter on equilibrium. So basically, Le Chatelier's principle helps us explain what happens to a system in equilibrium um, when it undergoes a disturbance in the equilibrium. And so the general rule is whenever a disturbance affects equilibrium, equilibrium is going to shift to reduce the effect of that disturbance. So for example, if we have a reaction, we add more reactant to the reaction, then equilibrium is going to shift in a way to consume the extra reactant to make more product until equilibrium is reestablished. And so what are some things that we can do to disturb equilibrium? So again, when we disturb equilibrium, Q does not equal K when it's disturbed. So that's what we mean by disturbed, is when we disturb it so that Q is no longer equal to K. So when it's disturbed, Q not equal to K. So what it does is then when Q is not equal to K, it's going to shift in a direction so that Q can become equal to K. And so things that can affect or disturb equilibrium are changes in the concentration, changes in the pressure or volume, the same, whether you change the pressure or volume. So for example, if you increase the pressure, it's the same as decreasing volume due to Boyle's law, which states the relationship between pressure and volume. And then also we can change the temperature. So for example, with temperature, with most fruits, most foods, we keep most foods in the refrigerator, at least perishable foods, most perishable foods in the refrigerator, because what you're doing is you're decreasing the food or decreasing the temperature so that the food doesn't spoil as easily. So for example, we have food plus heat spoiled food. So what we do is when we don't want to spoil our food, we take it into the refrigerator. And what happens in the refrigerator is we see a decrease. That's not a good arrow. We see a decrease in the heat because when you put the food in the refrigerator, there's a decrease in the heat. So as you remove heat, less of the food will get spoiled. However, when you put the food on the counter, let's say it's hot in the room, you're adding heat. So as you add heat, you make more spoiled food. So that's just kind of a basic example of Le Chatelier's principle involving heat. And so what do we mean by when we say the net reaction? So it refers to how the equilibrium is going to shift the position. Will it shift to the right? And that means, for example, make more products. or will it shift to the left, which means it makes more reactants. So when we say net reaction shifts to the right, the equilibrium is going to shift to the right to make more products. We say the net reaction shifts to the left, we're going to say equilibrium shifts to the left to make more reactants. And so concentrations or pressures change in a way that reduce the effect of the changing conditions so that the system attains a new equilibrium position. So for example, if we add more reactant, the concentration is going to change in a way so that we reestablish equilibrium, so it's going to make more product, for example. Back up. So now let's look at the first type of disturbance, which is change in concentration, and how that affects equilibrium. There are two things you can do to concentration. You can increase the concentration of a reactant or product, or you can decrease the concentration of a reactant or product. And so when you increase the concentration of reactant or product, the system is going to react to consume some of it. So that means it makes more of the other side of the reaction. So for example, if we have the equation A plus B yields C, if we increase A, so let's say we increase A's concentration, then it's going to system's going to react to consume some of it. So what does that mean? The system's going to react to make product. Now if we decrease the concentration of A, let's say we have the same equation, A plus B. Now if we decrease the concentration of A, it says that the system is going to react to produce some of it. So if we're decreasing a reactant, it's going to shift to make more reactants. So it's going to shift from products to reactants until equilibrium is reestablished. And so when we're adding a reactant, say for example we have the synthesis of phosphorus pentachloride, when we add a reactant, say Cl2, the reaction will shift to the products. Or equilibrium, the net reaction will shift to the products. So it shifts to products. Or we say shifts to the right. So when you add a reactant, you're going to make more product. But adding or removing a reactant does not involve solids or liquids. So if you're adding a solid or a liquid, there's no change in equilibrium. So don't fall for that one. So only aqueous and gases can affect equilibrium, not solids and liquids. Now when we remove a reactant, it's going to shift in the direction to make more reactant. So shifts to make reactants to the left. So in general, when you add a reactant or product, it's going to shift to the opposite side. So if you add a product, it's going to shift to reactants. If you add a reactant, it's going to shift to products until equilibrium is reestablished. When you're removing a reactant or product, it's going to shift to the side you're removing from. So if you remove a reactant, it's going to shift to reactants. If you remove product, it's going to shift to products. So removing is going to shift to the side that you're removing from. Adding shifts to the opposite side. So the green represents any change that causes it to shift to the products. And so that means increasing a reactant will shift to products, or decreasing a product, it will shift to products. Now on the bottom in red are those that will cause it to shift to the left. So of course, if we decrease a reactant, it's going to shift to the reactants. If we add product, it's going to shift to the reactants. So again, that does this to reestablish equilibrium. That's how concentration affects equilibrium. So let's look at some examples here. Which way will equilibrium shift when H2 is added to the following? So we're going to add H2 to each one of these reactions. Which way will equilibrium shift? So here in A, H2 is a reactant. So we're adding a reactant. Which way will equilibrium shift? That's right, to the products. So it's going to make more products until equilibrium is reestablished. So we say it shifts to the right. And the second example, H2 is a product. So if we're adding more product, which way is it going to shift? That's right, it's going to shift to the left to make more reactants. So we say it shifts to the left. Again, it shifts to the left until equilibrium is reestablished. Now in the last one, we don't have H2. So since there's no H2 in the reaction, there's no change. All right. Let's look at one more example, I believe we have. Oh, no, we don't. That's coming up later. So we talked about concentration. You add a reactant or product, it shifts to the opposite side. You remove a reactant or product, it shifts to that side. Now we're going to talk about pressure volume changes to a system at equilibrium. And this only affects those reactions with gaseous components. So if you don't have a gaseous component in the equilibrium equation, then pressure and volume will not affect equilibrium. So one thing we can do is add an inert gas. So an inert gas is things like helium gas, nitrogen gas, argon gas, neon gas. These are the most common examples. Now, when you add an inert gas, it has no effect on the equilibrium as long as the volume of the system remains constant. So if it says in the problem that we added an inert gas and there was no change in volume, then there's no effect to equilibrium. So all the concentrations and partial pressures are the same. And the inert gas does not appear in Q. Now, if it changes the volume, then you have to use the rules for changing volume or pressure of a reaction. But if it says no change in volume or pressure, then the inert gas does not affect equilibrium. So one thing we can do with gases is changing the volume. And whatever we say for volumes is the opposite for pressure. And this causes a large shift in equilibrium. And this only occurs for those reactions where the number of moles of gas changes. So that means when you look at the reactants and products, when you look at the total moles of gas on each side, they're not the same. So with reactions in which the moles of gas change, we have the following. We can reduce the volume or increase the pressure, either one. And equilibrium shifts to the side with fewer moles of gas. So if you reduce the volume or increase the pressure, it's going to shift to the side with fewer moles of gas. That makes sense because now there's less volume. So you want to pick the side that has less moles of gas. The other thing we can do is increase the volume, or the same as reducing pressure. And here equilibrium shifts to the side with greater moles of gas. That's because you're expanding, so there's more room for gas molecules, so you want to pick the side that has the more moles of gas. So here we look at this equation, the synthesis of phosphorus pentachloride. I guess there should be an arrow here. So this system's at equilibrium. So on the reactant side, we look at the coefficients: 1 mole of phosphorus trichloride, 1 mole of chlorine gas. That's a total of 2 moles of gas. And on the product side, we have 1 mole of gas. And so this is a net difference of -1. So if we increase pressure, it would shift to products, because products has a fewer moles of gas. If we increase the volume, shifts to reactants. As you increase volumes, it shifts to the side with more moles of gas. So now let's look at some examples involving gases. So here we have this following set of equations, and it wants to know which of the following would change in volume, not affect equilibrium. So we have these reactions, we want to know which of the following, if we change the volume, won't affect equilibrium. So there are two things we're looking for to not affect equilibrium. A is no gases in the equation. Number two, what we can look for is no change in moles of gases. So that's what we're looking for in this. So if it meets one of these two criteria, volume will not affect equilibrium. So now let's go through it. So in A, we have 1 mole of gas on the reactant side, 0 on the product side. So A could be affected by volume. Next, we have 2 moles of gases on the reactant side, 2 moles of gases on the product side. So here, no change in the moles of gas. So therefore, it would not be affected by change in volume. So that's one of the answers. Next, in C, no gases on the reactant side, but we have 1 mole of gas on the product side. In D, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So here, no change in moles of gas. So this will not be affected by volume change. And then lastly, in E, 1 mole of gas on the reactant side, 2 moles of gas on the product side. So the correct answers are B and D. They will not be affected by volume. Equilibrium will not be affected by the volume change in those two equations. So here we want to know which way will equilibrium, or we want to know which way will equilibrium shift by increasing the volume of the reaction vessel. So if we're increasing the volume, shifts to the side with more moles of gas. So what we're looking for in each one of these is which side of the equation has more moles of gas. That's the side it's going to shift to. So here we look in A, we have 2 moles of gas on the reactant side, 3 moles of gas on the product side. So this has 3, this has 2. So when we increase the volume, it's going to shift to products. So this shifts to products because you have more moles of gas on the product side. Next, we have 0 moles of gas on the reactant side, and we have 1 mole of gas on the product side. So since there's more moles of gas on the product side, when we increase the volume, it's going to shift to make more products. So it's going to shift to the products. Now we look at the last example. On the reactant side, we have 3 moles of gases. Oops, that's not a good 3. So on the product side, we have 3 moles of gases. On, the reactant side, we have 3 moles of gases. On the product side, we have 2 moles of gases. So if we increase the volume, it's going to shift to reactants. So again, increasing the volume causes it to shift to the side with more moles of gas. Decreasing the volume causes equilibrium to shift to the side with fewer moles of gas. So now temperature. And so for temperature, we're going to look at 2 types of reactions. We're going to look at endothermic reactions, and we're going to look at exothermic reactions. And it's best to think of temperature, think of heat. So think of heat as a reactant or product. And if you do this, it's very easy to understand how temperature will affect equilibrium. So for endothermic reactions, let's say we have A plus B. Endothermic heat is a reactant because you absorb heat. Gives us C. Exothermic reactions, heat is a product. A plus B, C plus heat. Heat is a product in exothermic reactions. So for endothermic reactions, heat is a reactant or a positive delta H. For exothermic reactions, heat is a product or a negative delta H. So let's look how temperature affects these types of reactions. So now let's look at the first. If we increase the temperature for an endothermic reaction. So if we increase the temperature of an endothermic reaction, what does that mean? That's correct. That means that we're adding heat. So if we're adding heat to an endothermic reaction, that means we're adding a reactant. And if you remember from earlier, if we're adding a reactant, it's going to shift to the products. So for an endothermic reaction, when you increase the temperature, it's going to shift to products. Now let's look at when we decrease temperature. So when we decrease temperature, we're removing heat. So that means heat is decreasing. So if heat is decreasing, that means we're removing a reactant. So we learned in the earlier slides, as we remove a reactant, it shifts to make more reactant. So this shifts to reactants. If you remember at the beginning of this lecture, we had the thing about food spoilage. So food plus heat gives us spoiled food. And if we put it in the fridge, if we place it in the fridge, what happens is we're removing heat. So if we remove heat, less of the food gets spoiled. So now let's look at exothermic reactions. So for exothermic reactions, heat is a product. So what happens when we increase temperature? So we have our reaction. So in an exothermic reaction, heat is a product. If we increase the temperature, so we're adding heat, it means we're adding a product. And as we learned about in the previous slides, when you add a product, it's going to shift to reactants. So it shifts to reactants. Now if we decrease temperature, let's look at our equation again. So now if we decrease temperature, so that means we're removing heat. And again, heat is a product. So as we learned early on, when you remove a product, is going to shift to make more product. So it shifts to the right. So now let's look at an example based on the food. We'll look at Jello. So I know it's about food, but food's always a good way everyone can relate to. So we have the Jello mix plus water gives us Jello plus heat. And let's say we're going to place this Jello mix in the fridge, which is what you do when you make Jello. You place it in the fridge so it solidifies. Let's see why using Le Chatelier's principle. So we place it in the fridge. The fridge, what does that mean? That means we're removing heat. If we remove heat, that means more of the Jello mix and water will become Jello. That's why the Jello solidifies. I mean, that's an example of why Jello solidifies in the fridge, because it removes the heat, causing the Jello to congeal. I don't know if congeal is the right word, but it causes the Jello to make Jello and to solidify in the fridge. I mean, it's a very simplistic explanation of the making of Jello. So that's how temperature affects equilibrium. It depends. First, is the reaction endothermic or exothermic? Endothermic meaning heat is on the reactant side or positive delta H. Exothermic meaning heat is on the product side, negative delta H. And so based on that, we look at heat. If we're increasing the temperature, we say we're adding heat. If we're decreasing temperature, we say we're removing heat. And we treat heat as a reactant or as a product. Let's look at some examples. So here we want to look at which of the following equilibria shifts to the left when temperature is increased. So if we think back about the previous slide, endothermic means heat is a reactant. And if we're increasing the temperature, it's going to shift to products, the right. We don't want endothermic reactions. Now if we look at exothermic reactions, heat is a product. So if we increase the temperature, it's going to shift to reactants. So what we're looking for are those reactions in which it's exothermic. So we're looking for heat as a product or a negative delta H. So A has a negative delta H. It will shift to the left when temperature is increased. B would not, because it's endothermic. It would actually shift to the right. So let's draw these. So this one would shift to the left. This one would shift to the right. Now in C, it's exothermic. It would also shift to the left. So exothermic reactions, when you increase the temperature, will shift to the left. Endothermic reactions shift to the right. Look at one more. So here we want to know which of the following reactions will increase reactants when temperature is increased. So we will know which ones will shift to the left. So again, endothermic reactions heat is a reactant When we increase temperature, it's going to shift to products. Exothermic reactions heat is a product, and that's going to cause it to shift to reactants as we increase temperature. So what we're looking for again is exothermic reactions. Those are the ones that are going to increase the reactants when we increase the temperature. So we look here in number 1, it's a positive delta H. That means it's endothermic. So if we increase the temperature, it's going to shift this way. So that's not 1. Next, we have a negative delta H. Since it's negative delta H, if we increase temperature, it's going to shift to reactants. So that is 1. In C, we also have a negative delta H. So that's going to shift to the reactants when we increase the temperature. So that is also one of the correct choices. Now the last one, we have hemoglobin, and it's endothermic. So if we increase the temperature, it's going to make more products. So the correct answers here are B and C. So one last thing is catalysts, and as we learned about early on in kinetics, catalysts lower the activation energy of a reaction. Since it lowers the activation energy of the reaction, both the forward and reverse reaction are sped up by the same extent. So catalysts do not affect equilibrium. So again, catalysts do not affect equilibrium. It just makes it easier for it to go the forward or reverse race. So catalysts do not affect equilibrium. Do not. So if we look at an overview of what we just talked about involving Le Chatelier's principle, for concentration, the thing we can do is we can increase or decrease reactants or products. So if we increase a reactant or product, it's going to shift to the opposite side. If we decrease a reactant or product, it's going to shift to the same side. Now with those reactions involving a change in the moles of gas, pressure can affect equilibrium. So if we increase the pressure or decrease volume, it's going to move to the side with fewer moles of gas. If we decrease the pressure or increase the volume, it's going to move to the side with more moles of gas. Now if we increase the pressure and there's no change in the volume by adding an inert gas, then equilibrium remains unchanged. However, if we do add an inert gas and there is a change in volume, then it's going to change equilibrium. Equilibrium will shift. And then we talked about if something is endo or exothermic, we can look at how temperature affects those reactions. And the catalyst has no effect on equilibrium. Now let's look at some examples. So here we have this combustion. This combustion reaction, which is exothermic. We want to know which of the following changes, disturbances to equilibrium would increase the amount of N2. And so N2 is a product, and again, it's exothermic because heat is a product. So we know which one of the changes we can do to increase the amount of N2. So what we're going to do is we're going to look and see which one, we're going to go through each one of these changes and see which way will equilibrium shift, and we'll come back and answer the question. So if we remove H2, H2 is a product, it's going to shift to products. If we increase the temperature, this is an exothermic reaction, we're going to be adding heat. It's going to shift to reactants. We increase the volume, it moves to the side with more moles of gas. So there's 8 on the product side, 7 on the reactant side. It's going to shift to make products because it has the more moles of gas. Adding water vapor, again, water vapor is a product. If we're adding a product, it's going to shift to reactants. Removing ammonia, ammonia is a reactant. If we remove a reactant, it's going to shift to reactants. Now the next one is a little bit tricky. Here we're saying what happens when we add HCl. And this has an indirect result. So what happens is when you add HCl, which is a strong acid, HCl reacts with ammonia to give NH4 plus and Cl minus. So when you add HCl, you're decreasing the concentration of ammonia. So since you're decreasing a reactant, it's going to shift to make more reactants. So the ones that will cause an increase in N2 are going to be removing a product such as H2O gas or increasing the temperature. The other ones will not increase the amount of N2. So sometimes they add things which perform it. They may not be involved in the chemical reaction, but they have a secondary reaction with one of the reactants or products. Here we have another equilibrium equation. So here we have this equilibrium where the reactant side is yellow, bicarbonate plus water. The product side is red, carbonate and hydronium ion. And if we see here, we have a positive delta H, so it's endothermic. The above reactions as equilibrium has an orange color solution, where red and yellow make orange. Which of the following would cause the solution to become more yellow? And yellow is on the reactant side. So we want to see which one of these disturbances will cause it to shift to reactants. So again, first thing we're going to do is see which way it's going to shift with each one of these disturbances. So decreasing a temperature. So decreasing a temperature means, that's correct, it means that we're removing heat. And since this is endothermic, heat is that's correct, a reactant. So if we're removing a reactant, it's going to shift to reactants. Next is adding a palladium catalyst. That's correct. Catalysts do not affect equilibrium, so no change. Decreasing the pressure. So decreasing the pressure means we have to have moles of gas present. But in this equation, there's no moles of gas, so there's no change in equilibrium. Adding HCl. Now this one's a little bit tricky. When we add HCl to water, we get the hydronium ion. So when you're adding HCl, you're actually adding a hydronium ion. Since you're adding a product, it's going to shift to make reactants. Adding NaOH. Again, this is a tricky one. So it's a secondary reaction. So if we add NaOH, the hydroxide of NaOH is going to react with the hydronium ion to form water. So you're removing hydronium ion, which is a product. So it's going to shift to products. Next, we have adding H2O. I'll give you a few seconds to think about this one. So which way will it shift if we add H2O? Dun, 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 dun. So the correct answer is no change. Because H2O is a liquid, it does not affect equilibrium. Finally, we have calcium chloride, and we have to look at this because this one forms, again, another indirect reaction. So from calcium chloride, the calcium 2 plus reacts with carbonate, -2, to form calcium carbonate, which precipitates out. So if the calcium reacts with the carbonate for it to precipitate out, that means we're losing carbonate, we're decreasing the concentration of carbonate. So that means it's going to make shift to the products. Adding helium gas, which is an inert gas, will not affect equilibrium. And secondly, it won't affect equilibrium even if you did change the pressure or change the volume because there's no gases in this reaction. So which ones will cause the solution to turn more yellow will be the ones shifted to the reactants. So that would be A, D, A and D. Look at another example. Here we know which one would cause C to increase in the following equation. So we know what's going to cause the concentration of C to increase, and it tells us this is a exothermic reaction. Let me draw the other arrow here. There we go. So adding a catalyst. Well, first we're going to, before that, excuse me, first we're going to see which way equilibrium shift with each one of these disturbances. So adding a catalyst, will that affect equilibrium? If so, which way? That's correct, it won't. So we'll just draw a line. Or we'll put an X, doesn't affect equilibrium. Removing B. B is a reactant. If we remove reactant, which way will it go? That's correct. It's going to shift to the reactants. Increasing the pressure. Increasing the pressure will shift to what side? That's correct, the side with the fewer moles of gas. And which side has the fewer moles of gas? That would be C. That is correct. So it's going to, or products. It's going to shift to product side. Removing AB. So AB is a product. If we remove AB, how will equilibrium shift? That's correct. It won't affect equilibrium at all because AB is a solid. Increasing the volume. So increasing the volume will shift to what? That's correct. The side with more moles of gas. So which side has the more moles of gas? That's right, the reactant side. Placing in a freezer. A freezer does what? That's correct. Removes heat. So if we're removing heat from an exothermic reaction, which way will it shift? That's correct. The products. Adding A. A is a product. A is a reactant. If we're adding a reactant, which way will it shift? That's correct. To the products. So all the ones that shift to the products will increase the concentration of C. So that would be C, G, and A. The other ones would shift to the opposite side or no change. So here we want to look at these reactions and see which one will increase the yield of products when we increase the total pressure of the reaction mixture. So when we increase pressure, shifts to the side with fewer moles of gas. So what we want to do first is to see which side each of these equations will shift to, and then we'll see which ones shift to the products. So if we look at number one has 2 moles on the reactant side, 2 moles on the product side. So this would have no change because you have the same number of moles of gases. In B, we have 2 moles on NO and 1 mole of Cl2. That's 3 moles on the reactant side and 2 moles on the product side. So if we increase the pressure, it's going to shift, that's right, to the products because it goes to the side with fewer moles of gas. In C, we have 2 moles on the reactant side and we have 3 moles. Oops, that's a bad 3. 3 moles on the product side. So if we increase the pressure, it's going to shift to the side with fewer moles of gas. It's going to shift to the reactants. In D, we have 2 moles on the reactant side, 2 moles on the product side. This would have no change in equilibrium because there's no change in the moles of gas. In E, we have 3 moles on the reactant side, and we have 1 mole on the product side. So for pressure, it's going to shift to the side with fewer moles of gas. So that'd be the products. Again, here H2O is a liquid. It won't be affected by equilibrium change, increase in pressure. In F, 0 moles of gas on the reactant side, 0 moles of gas on the product side. So this would have no change. So which ones will increase the products? That would be B and E. Look at one more. I think this is the last one, but hopefully you're getting the hang of it by now. Never hurts to do a lot of examples. So we have this reaction involving C, carbon plus water gives us carbon monoxide and H2. Gives us delta H here. Delta H is positive. This means it's endothermic. Which of the following will cause equilibrium to shift to the left? So if we increase the volume, which way will it shift? And that's correct. Increasing the volume shifts to the side with more moles of gas. And so from this, we have 2 moles on the product side and 0 moles on the reactant side. So this will cause it to shift to the products, or we would say to the right. Removing carbon, carbon is a reactant. So which way will it cause it to shift if we're removing a reactant? That's actually good. I'm glad you remember that. It means that there's no change because carbon is a solid. So it won't shift equilibrium. Decreasing the temperature. So this is an endothermic reaction, meaning what? That's right, heat is a reactant. So we decrease the temperature, we're removing what? That's correct, a reactant. So if we're removing a reactant, it's going to shift to make more reactant. Adding a catalyst, how will it shift? That's correct, no change, because catalysts do not affect equilibrium. Increasing the pressure. Now increasing the pressure, as we remember from earlier slides, moves to the side with what? Fewer moles of gas. So if we look up here, which side has the fewer moles of gas? It's the reactants. So it's going to shift to the reactants. Adding CO gas. CO is a product. When we add a product, it shifts to what? That's correct. Adding, it shifts to the reactants because we're adding a product. Adding an inert gas with no change in pressure or volume. That's correct. No change. Increasing the temperature. Again, this is an endothermic equation. Endothermic reaction means heat is what? That's correct, a reactant. So if we're increasing the temperature, we're adding more reactant, which is going to shift to what side? That's correct, to the products. And so the shift to the left means we're shifting to reactants. So which one of these shifts to the left? That's decreasing the temperature, increasing the pressure, adding CO. Oh, we got one more. I believe this is the last one. Yep. This is the last one. I know you're excited, you want to start the daily homework for this chapter. I understand. I'm almost done. One last one. So here we want to know which of the following would cause an increase in CO. And I forgot to mention here that this is CO is a gas. That's actually a pretty good G. So we want to decrease the volume. Decreasing the volume means what? That's correct. It moves to the side with fewer moles of gas. So this has 1 mole. This has 2 moles. So it's going to shift to the left. Removing CO. CO is what? That's correct, the product. When we remove products, which way is it going to shift? To the products. Adding more CO means we're adding a product is going to shift. That's correct, to reactants. Adding more graphite. Graphite is a reactant. So we add more reactants. Which way will it shift? I'll give you a few seconds to think about this one. So we're adding graphite. Which way will it shift? That's correct. It will not shift because graphite is a solid. Decreasing the pressure. When we decrease the pressure, it moves to the side with more moles of gas. So it's going to shift to the products. Adding a catalyst. What will catalyst cause it to shift to what side? That's correct. It will not cause it to shift. And increasing the temperature. Here the reaction is exothermic. Exothermic means what? That's correct. Heat is a product. If heat is a product, we're increasing the temperature. We're adding more heat. So since we're adding a product, it's going to shift to the reactants. So which ones would cause an increase in CO? Well, removing CO and adding, and it'll cause it to make more CO. I don't know if you would increase it. That one's a little bit gray area. And decreasing the pressure. So. So that's the end of today's lecture on Le Chatelier's principle. I hope by going through the principles and doing lots of examples, you grasp the fundamentals of how these disturbances affect equilibrium. And now you're all geared up, ready to do your daily homework. If you liked the video, make sure to click the like button or leave a comment. Thank you for your time. Until next time.